I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In continuation with my last lecture on water and its treatment, the next process for the purification of water or for the softening of hard water is the lime soda process. Now, this lime soda process is now obsolete, but it was very useful for the treatment of large volumes of hard water. The water which gets supplied to the household, it was treated by the lime soda method. In this process, the calcium and magnesium ions, not only calcium and magnesium ions, but also the heavy metal ions, they are precipitated by the addition of lime, which is calcium hydroxide, and soda ash, which is sodium carbonate. So, all these ions, they are converted into their precipitates by the addition of lime and soda ash, and this precipitate settles down at the bottom of the tank where we are doing the treatment, and thus they are separated from the water. Now, coming to the standard water softening process, it uses lime and soda ash to reduce the hardness of the treated water by precipitating the dissolved calcium and magnesium ions as insoluble calcium carbonate and magnesium hydroxide respectively. It also used in the precipitation of caustic soda by mixing slacked lime with soda and filtering of the precipitate of calcium carbonate. This process can be carried out either in the cold or hot. Now, coming to the differences between cold lime soda and hot lime soda process. As the name suggests, one takes place at room temperature, that is around 25 to 30 degrees centigrade, while in the case of hot lime soda process, it is carried out at high temperatures. The temperatures can range from 95 degrees centigrade to 110-120 degrees centigrade. So, the cold lime soda process, since the viscosity of water is high at the lower temperature, therefore it is a slow process. But hot lime soda process is a rapid process. In cold lime soda process, we require coagulants. Coagulants like alum, like aluminium sulfate, they are required so that they can generate the gelatinous precipitate of aluminium hydroxide, so that the different particles which are formed of precipitate, they coagulate with each other and form the denser particles, and they can get settled down at the bottom of the water tank. But in the case of hot lime soda process, we do not require the coagulants. Precipitation is a rapid process in case of hot lime soda process, therefore we do not require the coagulants. In cold lime soda process, the filtration process is not easy, but in the case of hot lime soda process, filtration becomes easy as the viscosity of the water is lowered. The residual hardness which is left after the cold lime soda process, it is around 60 ppm. But in the case of hot lime soda process, the residual hardness which is left after the treatment is around 15 to 30 ppm. In the cold lime soda process, the dissolved gases, they are not removed, whereas they get removed in the hot lime soda process. So, the softening capacity in the case of cold lime soda process is not very high. It has low softening capacity, but the hot lime soda process has high softening capacity. If we carried out the lime soda process at room temperature, then it is known as cold lime soda process. And here I am showing the two different types of cold processes. First is the batch process and the second one is the continuous process. In the batch process, in a tank we have taken the hard water, and we take the hard water, we add the chemicals which are lime and soda and coagulants, and there is a mechanical stirrer. It mixes water with the chemicals and as a result different ions, they get precipitated and they keep on settled down at the bottom of the tank, whereas the soft water, it is taken out from the softened water outlet. So this sludge precipitate which is being formed, it is removed from the bottom of the tank, and after the whole soft water is taken out, this tank is cleaned and again the process is repeated. Therefore, this process is known as batch process. Whereas in the continuous process, we keep on adding continuously raw water and the chemicals which are soda, lime and the coagulants. So we keep on adding and we add in the inner chamber of this continuous process. There is a mechanical stirrer, it stirs and it mixes the water with the chemicals. So the combination of water with the chemical takes place here, and since due to stirring, the soft water, it moves upwards, whereas the sludge formed, the precipitate which is being formed due to the precipitates of calcium carbonate, magnesium hydroxide, iron hydroxide, aluminium hydroxide, it gets settled down at the bottom. And the soft water, after passing through wood fiber filter, it moves out from the outer chamber, and this sludge, it is removed from the sludge outlet. So this is how the continuous process runs and we get soft water. So coagulant, it is necessary in cold lime soda process because at room temperature precipitate is finally divided. Therefore, it does not settle down easily and they cannot easily be filtered off. Therefore, one coagulant, sodium aluminate, is added. It mixes with water to produce NaOH and the precipitate of aluminium hydroxide. And mechanical stirrer is used to increase mixing and the rate of precipitate formation. Aluminium sulfate or sodium aluminate, they are used as coagulants in lime soda process in order to help formation of coarse precipitate. As coagulation is a process of adding coagulant to destabilize a stabilized charged particle. The residual hardness in the lime soda process is around 15 to 50 ppm, and in the lime soda process, softness cannot produce a water which is completely free of hardness because of the low solubility of calcium carbonate and magnesium hydroxide. So the water cannot be 100% free from hardness. There is going to be residual hardness, which is because of the low solubility of calcium carbonate and magnesium hydroxide. Now coming to the hot continuous process. In the case of hot lime soda process, the continuous one, there is an inlet for the raw water. Then there is an inlet for the chemicals. Here the chemicals include only lime and soda and not the coagulant. We do not require coagulant in the hot lime soda process. And in addition to these two, there is a third inlet which is for the superheated steam inlet. So these three mix here and they move towards the reaction tank. As a result, the reaction starts. Formation of precipitate takes place quickly. The precipitates settle down and the soft water moves out from this tank to the sand filter. The soft water moves out from this tank to the sand filter. Now this sand filter, it consists of different layers of sand. The first layer of sand is the fine sand layer. Then there is coarse sand layer, and finally there is a layer for the gravel. So this soft water, it passes through these three layers so that if any particles of precipitates come out along with the soft water, then they get settled down here, and finally the filtered softened water is taken out from the water outlet. So there are three chambers here. One is the reaction tank, then the sedimentation tank where the sludge settle down, and finally the filter. So, filtered water is removed from the system. So, this process, it is carried out at a temperature of around 80 to 150 degrees centigrade, and it is used when small quantities of water is required. But it takes place at low hardness, that is around 15 to 25 ppm. Due to hot conditions, reaction it takes place at a faster rate. Then we do not require the coagulant. That means our needs of chemical get reduced. Residual hardness is low, lower than the cold lime soda process, and along with that the dissolved gases, they are expelled out at high temperature. Coming to the basic principle, now the lime and soda, they are the reagents which are used to precipitate the dissolved salts of calcium, magnesium as calcium carbonate and magnesium hydroxide. Now, these precipitated calcium carbonate and magnesium hydroxide, they are filtered off. Now, lime reacts with the temporary hardness, that is bicarbonates, CO2, acids, alums. Lime cannot remove the calcium permanent hardness, which is then removed by the soda. The precipitation reactions with lime and soda are very slow, and we add lime and soda only in calculated amounts, because the excess of amounts of lime and soda, if present in the boilers, they are going to cause the boiler troubles like caustic embrittlement. Now, these are different reactions, that is the treatment with lime. Now, we can remove the temporary hardness of calcium with lime. Now, here you can see in this equation, this is calcium bicarbonate. If it is present in hard water, then lime, which we are adding in water, reacts with calcium bicarbonate to form the precipitate of calcium carbonate and water. Our ultimate aim is to convert the hardness causing impurity into their respective precipitates. So, calcium has to be converted into calcium carbonate. So, by this reaction, the entire calcium which is present, it is getting converted into calcium carbonate. So, according to this equation, you can see 1 mole of calcium bicarbonate requires 1 mole of calcium hydroxide for its complete neutralization or conversion into the precipitate. So, 1 mole means, suppose the molecular weight of calcium bicarbonate is 162 and the molecular weight of calcium hydroxide is 74. That means 162 grams of calcium bicarbonate requires 74 grams of calcium hydroxide for its neutralization, or 162 milligrams of calcium bicarbonate requires 74 milligrams of calcium hydroxide. And if in water, this calcium bicarbonate is present in X milligram per liter, then according to this equation, 162 milligram requires 74 milligrams of lime. So, X milligram will require how much lime? So, we can calculate the amount of lime required by calcium bicarbonate. So, X will require X into 74 divided by 162. Similarly, removal of temporary hardness of magnesium ions. So, magnesium bicarbonate, 1 mole of magnesium bicarbonate for its neutralization requires 2 moles of lime to form magnesium hydroxide precipitate and calcium carbonate precipitate plus water. That means, if magnesium bicarbonate, its molecular weight is suppose 136, then 136 gram require 2 into 74 grams of calcium hydroxide. because 1 mole is requiring 2 moles. So, molecular weight, this molecular weight will require 2 into molecular weight of calcium hydroxide, and X will require how much? So, according to the mole concept, we can calculate for individual salts how much lime and soda will be required by them. Similarly, for the removal of permanent hardness of magnesium, these are the different reactions. You can see 1 mole of all the salts are requiring 1 mole of lime. Next, removal of CO2. The dissolved gas CO2 which is present, it requires 1 mole of lime to form the precipitate of calcium carbonate. So, CO2 is 44. So, 44 grams requires 74 grams, and if X milligram is present in water, then how much will it require? These are the reactions for the removal of acids. Here you can see 2 mole of HCl is requiring 1 mole of lime. But in the case of sulfuric acid, 1 mole of sulfuric acid will give you 2H plus. So, 1 mole requires 1 mole lime. In the case of HCl, 2 moles are reacting because 2H plus will be given by 2 molecules of HCl. Therefore, 2 HCl will require 1 mole. But in the case of sulfuric acid, both the H plus, they are given out by 1 mole of or 1 molecule of H2SO4. Therefore, 1 mole H2SO4 requires 1 mole of calcium hydroxide. These are the removal of bicarbonates of sodium and potassium. These are the reactions. Removal of alums, these are the different reactions. Here, 1 mole of ferrous sulfate requires 1 mole of lime, whereas 1 mole of aluminium sulfate requires 3 moles of lime. So, these are the different reactions. Treatment with soda. Similarly, when we are going to treat our hard water with soda, then how the different reactions or how the precipitate formation will take place. First is the removal of permanent hardness of calcium. Whether the calcium is present in the form of calcium chloride or calcium sulfate or calcium nitrate, they all are going to react with 1 mole of soda to form their precipitate. Now, coming to the calculation of lime and soda required for the process. This is the total requirement amount of lime required for softening. It will be 74 divided by 100. Temporary hardness of calcium, 2 into temporary hardness of magnesium, permanent hardness of magnesium, then CO2, then half of HCl, full of H2SO4, half of sodium bicarbonate, half of potassium bicarbonate, ferrous sulfate, 3 into aluminium sulfate minus half of sodium aluminate. We have calculated this from these equations. For aluminium sulfate, you require 3. From sodium aluminate, you can see it is producing NaOH. Now, this NaOH functions similarly as calcium hydroxide. That means, suppose magnesium sulfate is present. Suppose in my water magnesium sulfate is present. Then if I require lime for its neutralization so that magnesium hydroxide is being formed, instead of lime, I can do the same reaction with 2 moles of NaOH. If I react magnesium sulfate with 2 moles of NaOH, then the reaction will be formation of the precipitate of magnesium hydroxide and Na2SO4 will be formed. So, here since NaOH is being produced in the as product, therefore, NaOH is going to work similarly as the function of the lime. So, here if this sodium aluminate is present in water and it is producing NaOH, then I need not add extra amount of lime. This much amount of lime will get reduced from the system because NaOH is functioning like lime and it is doing the same reaction which lime was supposed to do. So, ultimately my requirement of lime will get reduced. Therefore, in this reaction, I am not adding the requirement for lime. Instead I am subtracting the requirement of lime, because NaOH is automatically being produced as a product in the system. Similarly, the amount of soda required for the softening, since the molecular weight of soda is 106, so it is 106 by 100. Permanent hardness of calcium plus permanent hardness of magnesium plus half HCl plus H2SO4 plus ferrous sulfate, then 3 aluminum sulfate minus sodium bicarbonate minus half potassium bicarbonate. So, all these reactions, they have been, or the requirements, they have been calculated from these previous equations wherever they are required. According to their requirement, we have put in a concise equation form, and all these, they are in the terms of chemical equivalents of calcium carbonate after converting them into the chemical equivalents of calcium carbonate. Coming to the advantages, this process is more economical because it is economical. Why? Because the lime and soda, they are cheap chemicals. Then next advantage is less amount of coagulant is required, but it increases the pH value. As a result, the corrosion is reduced, because corrosion takes place in acidic conditions, more in the acidic conditions. Iron, manganese and minerals, they are also reduced. Pathogenic bacteria also get reduced in the alkaline water. Disadvantages, there is residual hardness. For example, 50 to 60 ppm of residual hardness is there in the in cold lime soda process, and around 15 to 30 ppm hardness is left in the hot lime soda process. And there should be careful operation and skilled supervision is required. And the disposal of large quantity of sludge which is being formed during the process is itself a problem. Now, here I have taken one numerical. Calculate the lime and soda needed for softening 50,000 liters of water containing calcium sulfate 136 milligram per liter, magnesium chloride 95, magnesium bicarbonate 73, calcium bicarbonate 162, and the given is the molar mass of calcium bicarbonate is 162 and that of magnesium chloride is 95. So, here I am going to write down the different constituents which are present in the water. So, the 4 different constituents which are present here are calcium sulfate, magnesium chloride, magnesium bicarbonate and calcium bicarbonate. These are the different amounts which are present in the water. These are their molecular weights, and equivalents of calcium carbonate, if I convert them into calcium carbonate equivalents, this comes out to be 100, this comes out to be 95, this comes out to be 50 and this comes out to be 100 again, because converting them into calcium carbonate equivalents, amounts which are present in the water, here it is 136. So, 136 into 136 into 100 divided by 136. So, on cancelling 136 by 136, it comes out to be 100. Similarly, we are going to calculate for the other amount which is present in water multiplied by molecular weight of calcium carbonate divided by the molecular weight of hardness causing substance. So, these are the different calculations, and we are going to calculate the lime. Now, lime is being required. The lime is required by the magnesium chloride. It is required for magnesium bicarbonate and calcium bicarbonate. How we have determined this? We have determined these from these equations. Calcium bicarbonate requires lime, magnesium bicarbonate, magnesium chloride requires. So, for these three, we are going to do the calculation, and we get that the lime required per liter is 296 milligram. So 296 milligram is required for 1 liter of water, and the water that we are treating is 50,000 liters. So for 50,000 liters of water, it is 50,000 into 296. That means 148 kg of lime will be required for the softening of water. Coming to the soda calculation. Now, soda requirement, you see, permanent calcium requires soda, and in this case, magnesium chloride on reaction with lime, it produces magnesium hydroxide precipitate, but it also produces calcium chloride in the reaction. Now, this calcium chloride which is being produced in this reaction, it need to be again converted into the precipitate of calcium carbonate. Therefore, this magnesium chloride will require 1 lime, and because this is being formed, therefore for its neutralization it will require 1 soda also, so that it can get converted into the precipitate of calcium carbonate and 2 NaCl is being formed. So we require, for magnesium chloride, we require lime also, and we require soda also. So in this numerical, soda will be required by permanent calcium and magnesium chloride also. And on this calculation, total comes out to be 212, and for 50,000 liters of water, if we multiply 212 with 50,000, we are going to get 10.6 kg of soda will be required for the softening of hard water. Now, the next method or the last method is the internal treatment method, which is the Calgon conditioning. Now, the Calgon means calcium, that is the removal of calcium ions, and Calgon is sodium hexametaphosphate. It reacts with the calcium ions and it forms a water solute compound which is converted to scale, which on drying, converted to scale, reduces the efficiency of the boiler. So our idea is to keep this calcium ions in the solution form so that they do not move out as precipitate and reduce the efficiency of the boilers. So here, this Calgon, we treat Calgon, it reacts with the calcium ions and it keeps the calcium ions in the soluble form. It does not let the calcium move out as the precipitate. At higher temperature, this Calgon, it is converted into sodium orthophosphate, which also reacts with the calcium ions, and it forms a loose sludge of calcium orthophosphate, and this sludge, it is removed by the blowing air. So here you can see this is the Calgon. The Na is being removed and the ions are being produced. This react with the hardness causing ions, that is the calcium ions, to produce the orthophosphate, which is a soluble complex ion. So these calcium ions, they do not move out as precipitate, they remain in the solution form, and this is the main functioning of the Calgon, so that the scale formation does not take place, otherwise the scale will start getting deposited in the inner walls of the boiler and hence the efficiency of the boiler will be reduced. So these conditioners or the Calgon conditioner, it is added in the water inside the boiler so that it softens the water but does not let the hardness come out as precipitate. Thank you.